Hello again. We are back with another video. This time it is an ideal Brayton refrigeration cycle. Example 10.43 in the 6th edition. If you need to see the values, just pause it at the beginning, but besides that, we're going to start right now. I didn't say get right into it. I caught myself. And so the first state, we have pressure 1 going into the compressor is 100 kilopascals. And temperature 1 as 270 degrees Kelvin. And we're using, this is air. This is a gas power cycle, or a gas refrigeration cycle. But we model gas as just ideal air. And so you go to the air table, and you find that H1 is equal to 270.11. The air table in this book is A.22, or A-22. Alright, and then we solve for state 2. And so we have to find PR2, because we have a pressure ratio in the problem, but we need PR2 to fix state 2. And so we know that PR2 over PR1 is equal to the pressure ratio. So if we move over PR1, multiply by the pressure ratio, which is 3 in this problem, you get a PR2 value to be, I don't know, a little less than 2, I think. Or a little less than 3, that's what I meant to say. A little less than 3, 2.877. It took me a minute to find it, I think, whenever I was doing it. As the pressure ratio, or relative pressure. And so, we move on to state 3, or well, state 2 continued, I guess. We're using the pressure, or PR2 value that we just found to find H2. And so, our H2 value is equal to, drum roll please, 370.101. With the circle. And now we move on to state 3. State 3, we have a temperature of 310 degrees Kelvin, which is, for ideal air, all we really need to find our H value. Once again, the air table, A22. And we know that we can find our H3 to be about 310. Little trick, if you're short on time, if you're in the lower temperatures in the air table, like 270, 280, 290, all the way up to a certain degree, like 400, your H values are almost the exact same number. So 270 is like 270.11. So if you're in a crunch for time, you can just drop that as your answer. Your temperature is almost equal to your enthalpy. But don't do that if the temperature is higher, like you start getting like 800, it doesn't work. There's a difference. And so now we move on to state 4. So for pressure, our PR4 over PR3 is equal to, or no, it should have been the other way around. It's PR3 over PR4 is equal to the pressure ratio. But I just know that it's dropping in pressure. So you know that you have to divide your pressure ratio by, or your PR3 by your pressure ratio to get it to a lower pressure, because we are going through a turbine on state 4. Which means we are reducing in pressure by definition. And so PR4 is equal to our PR3 value divided by our pressure ratio. Basically, it doesn't matter which way you write your PR over PR3, PR4 or PR3. If you just know what's going on, it doesn't really matter as long as you know that the pressure drops. And so you have to, you know that your PR value at 4 cannot be greater than the PR value at 3. But if it's a compressor, it's the other way around. It's PR2 has to be greater than PR1. And using that PR4 value, you get an enthalpy of 226. Now I move on to the solution. And so the first one is the work net of the cycle, which in this cycle, it is the work of the turbine, but I think I have a change of heart here, but just to make things easier for you, halfway through, I think I change it, because this is just the way that I think about it. It doesn't really, once again, direction for me doesn't matter because I know what it is. But if you aren't as versed, in this, you may not know. But as you can see, if you did this right here, you wouldn't get the direction of the work. You would get a positive work, which could probably confuse the hell out of you. And so I decided to go back the other way. I was like, you know what? I'm just going to do it the way that shows the direction better. And then everyone can see that the work net of the cycle has to be negative here, because the turbine does not create enough work to power the compressor. And so you end up getting a negative work of 16.003, which means that work was required for the cycle. It means something else has to come in. The turbine can't do it all. Something else has to happen. You must put in some work into the compressor. And the reason I didn't do it the other way around is because you'd get a positive work, and someone might think that this cycle is creating work, but it is not. And then part B, we are asking for the QN, the heat end of the cycle, heat removed from the refrigerated space. Which is H1 minus H4 by definition. But we don't have a mass flow rate in this problem, nor can we solve for one, so we're doing it all per mass. And if you put in your enthalpy values there, you will get H1 minus H4 to be 43.858 kilojoules per kilogram. Part C, we are solving for the COP of the cycle. Which is the heat in divided by the work of the cycle. But remember, for our problem, work of the cycle includes the turbine. So if you didn't find the work now, let's say you didn't yet, if you did it right here, you would have to include the turbine, like I'm about to show. You must show that it should be H3 minus H4 minus H2 minus H1. But if you do it like this, you will get a negative COP. I'm fairly certain, because obviously the bottom will be negative, but you just know to flip that to a positive. Because even if your COP is wrong, let's say you got a COP that was wrong, you can't have a negative COP. So just flip it anyway. But that is not wrong. And the last part is asking for a Carnot COP, which is the Carnot cycle equivalent operating between these two reservoirs, temperature hot and temperature cold, 310 and 270 respectively. And the COP of a Carnot cycle operating between these reservoirs is TC divided by TH minus TC. And if you input those in there, you get 6.75 as your Carnot COP. And the differences here, might make for a good question on an exam. Who knows? It was asked in the homework, but the difference between these two, it is losses in the heat exchanger. Because we assumed this problem that all turbine and compressors operated isentropically, so you know that there are no losses in those two. So it has to be the heat exchanger. The heat exchanger is not exchanging is not holding on to the heat perfectly. Apparently, that's the only way that this works. The Carnot assumes that it does. And so you can see the difference here. The Carnot obviously not going to work, but beside that, this is the end of the video. Thank you for watching.